All right, good afternoon once again, and today we're going to be looking at section 7.8, which is going to be improper integrals. Now, there are a few definitions and a few theorems that we're going to have to go over to make sure that we understand what's a process once we get to evaluate these improper integrals. On the screen here, you have the definition straight from your book. That says that this is a definition of a type 1 integral. Now, what does it mean to be a type 1 integral? Or in this particular case, what is it that we're going to be observing? All right. So when we're looking at a type 1 integral, I want you to observe the limits. It's saying that the limit as t goes to infinity or t goes towards negative infinity. We want to get a visualization of what's happening there. So I'm going to go back and I'm going to rely on my friend GeoGebra to get us to that part. So here we are. As we're looking at a type 1 integral or a type 1 improper integral, we're going to start identifying. Could we possibly find this integral for this function, which is the natural log of x divided by x squared, and say that we were integrating from 1 all the way to, let's say, 7? Sure we can. But what if we didn't stop at 7? What if we went to 8, or to 9, or to 10, or to 11, or to 12, so on and so forth? Right? Our minds can just keep taking all of these integrals or all of these values towards infinity. Which means, could we integrate this function with respect to x even if this function never ends? That's the process that we're looking at. If the answer is yes, well then that's a type 1 improper integral. Now, it might be that we cannot integrate it because this tail end doesn't get small fast enough, meaning that the area contributed will just keep on growing and growing and growing. This tail actually gets smaller and smaller and smaller, which means as we keep going towards infinity, these areas that we keep adding just basically keep totaling to a certain amount, and we can't add any further. A different type of a type 1 integral is this. Now, if you've ever taken some sort of a statistics course, you might see this as some sort of bell curve or a standard normal curve, and you'd almost be correct. It's a different manipulation of this, but you're on the right track. But essentially, the tails here, they go on forever, to the left and to the right. However, we want to try to see if we can calculate what is that total area underneath the curve, even though our tail ends go towards infinity. Could we still do it? That is what a type 1 integral, type 1 improper integral is. A type 2 improper integral, and we'll get to it in a bit, but I want to show you the visualization. A type 2 integral, say that I wanted to find the area for this integral. There's a problem with this integral. What's the problem? Well, the problem is that there's an asymptote right smack in the middle. According to Calc 1, we can only integrate for continuous functions. So we have an issue. This function is not continuous. However, could we establish this as an upper limit, not as my integral, but an actual limit that my limit will then approach? If the area can be calculated, then yay. If it cannot, then, well, boo, right? We're going to have more actual verbiage rather than yay and boo to actually go through these integrals. So therein lies type 1 and type 2 of these improper integrals. So what we want to do next is we actually want to jump into it and start using those techniques that we were just talking about that I wanted to develop. So let's go ahead and jump into it. All right, so that terminology that I was talking about, is going to be here, that an integral can either be convergent or it can be divergent. If when we're evaluating these integrals, the limit exists, well, then it's going to be convergent because the area will converge to a certain amount, meaning that we will be able to calculate it. If the limit does not exist, then by the limit not existing, that means that the area will not be, we will not be able to get a calculation for the area. Therefore, we are going to say that the integral is divergent. So that is a terminology that we want to work with. Is an integral convergent or is it divergent? All right, so let's try an example here. On this example, we want to determine whether each integral is convergent or divergent. So part A, we're going to work with the integral from 0 to infinity for 1 over, for 1 over the fourth root of 1 plus x. There we are. Whoops. Over here trying to erase this. There we are. There we go. And this is all going to be dx. So we now want to go through and we want to evaluate this. We want to determine if this is going to be convergent or if this is going to be divergent. All right. So let's go through our different techniques to see if we can evaluate this. So I'm going to go through and identifying here, I'm not going through any discontinuities, so this automatically fits a type 1 type of improper integral. So I'm going to say here type 1 improper integral. Oops, excuse me. There we are. So type 1 improper integral. So what I'm going to do is I'm going to fix this really quick, and I'm going to evaluate this using what I have up in that description. So this is from 0 to infinity for 1 divided by the fourth root of 1 plus x, and this is all dx. All right, I'm going to say that this is equal to the limit as, and then we can pick any variable that we want. You can go with u, t, m, n, whatever it is that you'd like. I'm going to, in this case, use t. So t, I'm going to send this to infinity. And this is going to be for 0 up to that variable substitution that I made. And this is going to be 1 divided by the fourth root of 1 plus x. And this is all dx. There we are. So now as we're working through this, we can then go through and we can say, okay, well, now all I need to do is make some sort of substitution to try to evaluate this. So I can choose my substitution here as u is going to be 1 plus x, then du is equal to dx, and therefore this is going to be the limit as t is approaching infinity, and this is going to be from 0 up to a certain amount. We'll get there in a little bit. I'm actually going to hold this as a placeholder. I'm going to say this is going to approach some a value, and again I'll put a pin on that as to what that means. All right, so here we go. This is now going to be 1 over fourth root of u, and dx, that was that du, which means this actually looks quite nice. 0 to a, and this is going to be u to the power of negative 1/4, and that's du. And the way we evaluate this is by, power rule. We add 1, so this is going to be, so when we add 1, this is going to be 4 over 4 plus negative 1/4, so that's going to be 3/4. and then divide by that exponent, but dividing would be the same thing as multiplying by its reciprocal, so that's going to be multiplying by 4/3, evaluated from 0 over to a. And again, a is just a placeholder that I'm using, and the reason I'm using a as a placeholder is because when I substitute in my u value for that upper bound of t, I really don't know what that upper bound of t is going to be. All right. So what I want at this point in time is my substitution. I'm going to use back substitution here, so that's going to be 1 plus x to the power of 3/4. And now I can say this goes from 0 to t. So now all I have to do is evaluate this. Well, 4/3, that's going to be a constant, so 4/3 multiplied by the limit as t goes towards infinity. And this is now going to be evaluated with 1 plus t to the power of 3/4 minus 1 plus 0 to the power of 3/4. There we are. So let's see if we can simplify. This is 4/3 multiplied by the limit as t goes to infinity. And this is going to be, well, that's just the 4th root of 1 plus t to the power of 3. And this is just minus 1. There we are. So as we take this limit towards infinity, these t values get very large. Because these t values get very large, we're going to cube them, and then we're going to take the 4th root of them, and then we're going to subtract by 1. Meaning these values, t is going to infinity, so imagine 100, 1,000, a million, a billion, a trillion, so on and so forth for those t values. That one's going to be very tiny, which means this is still going to head towards infinity. Now, what does that mean for us? Well, at this point in time, this goes towards infinity, and it's multiplying by 4/3, but still multiplying by infinity. Sorry, it's still going towards infinity. So, naturally, this means that the limit does not exist. Limit does not exist. Well, what does that tell us about our integral? Well, to then summarize this, we're going to say that the integral from 0 to infinity for 1 over the 4th root of 1 plus x dx is divergent. Divergent, again, means that it does not exist. So there we are. The first integral, part A, done. It is divergent. All right, let's work on part B now. All right, so working on part B. For part B, we want to evaluate this integral from 2 to infinity for the function y e to the power of negative 3y, and this is going to be dy. All right, so let's work through this evaluation. So again, I'm going to go through and I'm going to rewrite this. All right. Again, as I'm looking at this is an improper integral type 1. So this is type 1 improper integral. All right. Now, because it's type 1 improper integral, I'm going to say, let's choose a different value. Last time we chose t, we could choose, let's say, b in this case. So let's say b goes towards infinity. And this will be the integral from 2 going all the way to b. Nice. Let's erase that. There we go. And this is y e to the power of negative 3y dy. And now we can use any technique of integration that we've developed so far to try to simplify this integral or try to evaluate this integral. So, as I'm looking at this, I can try u substitution, but u substitution doesn't look that promising. I think I want to use by parts here, so I'm going to try by parts. So I'm going to try by parts. All right. I don't like those parentheses. Okay, so I'm going to try by parts. So that means I need to choose 2 different values. So let's say u is y, because then that means that du is just dy. dv is going to be everything left over, negative e to the power of 3y dy, and that means the antiderivative needs to be negative 1/3 e to the power of negative 3y. And we can double check if we take the derivative here, derivative stays the same, and then this, we take the derivative because of the chain rule. Negative times a negative is a positive. 3 divided by 3 gets me a 1. Perfect. So by parts means I multiply those two, so let's see. Equals the limit as b goes towards infinity, and this is now going to be u times v, so that's going to be y times negative 1/3 e to the power of negative 3y minus the integral, and that's from 2 to b of v du, so it's going to be negative 1/3 e to the negative 3y dy. And I do believe that is way easier to evaluate integral-wise. Limit as b goes towards infinity. This is now going to be negative 1/3 y e to the power of negative 3y. And I'll evaluate all of this from 2 to b in just a little bit. Negative times a negative, so it's going to be a positive so far. But then I need to take a derivative again. So this is going to be, I'm going to say negative 1/9 e to the power of negative 3y, all evaluated from 2 to b. And that's a positive, so that's a negative. All right, so that when I integrate, yeah, looks good. All right, so let's evaluate this now. We're going to go to the limit as b goes towards infinity, and this is going to be 1/3. The y values are what we're evaluating, so this is going to be b times e to the power of negative 3b minus 1/9 e to the power of negative 3b plus 1/3 times 2 times e to the power of negative 3 times 2. Negative times a negative, that's going to be a positive, so it's positive 1/9 e to the power of negative 3 times 2. All right, looking pretty good. Let's simplify these a little bit more. That way we can see what's really taking place here. Now, some of you might be able to see what's taking place, and that's perfect. That's why we went through chapter 6. So if we can't see it just yet, then that's okay. Here we're going to have b, or let me actually rewrite this, this first one here. This is going to be negative, and we're going to have b divided by 3, and that's e to the power of 3b. This one's going to be minus 1 over 9e to the power of 3b. This one's going to be plus, that's going to be 2 divided by 3 e to the power of 6 plus 1 over 9 e to the power of 6. There we are. All right, so it's looking pretty good. Now, we're going to go ahead and we're going to send b off to infinity. So, follow me on this. As b gets large here, the exponential is going to get very large, but that means the denominator is getting large. If the denominator of a fraction is getting very large very fast, then that means this goes towards 0. This one. b is going towards infinity, awesome, divided by e to the power of 3b. Again, this is going towards infinity as well. We can use L'Hopital's rule here since we have infinity divided by infinity, or we can go through the argument that the denominator is actually going towards infinity faster because these values are going to grow insanely large faster than b, which means denominator is going to beat out the numerator to get to a large number faster, which means this still goes to 0. So what are we left with once we evaluate that limit? We're just left with these two values. All right, well, let's see. That's 2/3. And I'm going to rewrite this as e to the power of negative 6 plus 1/9, and that's e to the power of negative 6. That means I can go ahead and add these values. So that's going to be 3 and 3, that's 6. Perfect. So that's going to be 7/9 e to the power of negative 6. There's our answer. So this integral is convergent. So the integral from 2 to infinity for y e to the negative 3y dy is convergent. And again, it's convergent because we are able to evaluate the limit once we're able to get to that part. If the limit exists, then the integral is naturally convergent. There we are. Nice. So if you want to take a pause really quick, I'm going to go ahead and I'm going to upload the type 2 integral definitions that we need. All right, so here we actually get to see the definition for that type 2 improper integral. And again, that type 2 improper integral, what we're going to do is we're now going to be able to evaluate these integrals that have this discontinuity or this asymptote within the interval that we're trying to integrate. So in Calc 1, we came up with a strategy that said we can only integrate so long as the function is continuous on the given interval. In this particular section, we don't have to do that. We can actually go through and say, hey, at this point in time, even if there's a discontinuity within the interval, all we have to do is break it up for that discontinuity and see what happens. So let's go through an example. We want to determine whether each integral is convergent or divergent. And needless to say that if it is convergent, we'll find that value. Part A, we're going to go from, we're going to go from -1 to 2, and this is going to be for x divided by 1 plus x squared, and this is going to be dx. All right, so we want some technique or something to break this apart. All right, so let's see if it's convergent or divergent. The first thing that we're going to see, the limits here from -1 to 2, they don't go towards any type of infinity. That's what lets me know that it's not a type 1 integral. The fact that the denominator is not continuous at -1, so the function that we're working with, which is this function, is not continuous at x is equal to -1, because again it makes the denominator undefined. Since that's the case, this is a type 2 improper integral. So let's go through and let's evaluate this then. Or let's actually develop the process for it. We're going to do the limits as, let's choose a different variable. We choose A, B, C, whatever we want. All right, last time I chose T and B, let's go with A. So A is going to approach -1, and we're going to be very, very careful here because our interval is only approaching it from one side. This interval is from -1 to 2, which means we're going to approach -1 from the right-hand side. All right, so now that we have this, we're going to say that's going to be for the integral going from a up to 2, and this is going to be for x divided by 1 plus x squared dx. There we are. So now we have to go through and find this evaluation, see if we can do it. All right, so I believe partial fraction decomposition will work here. All right, so if we want to try partial fraction decomposition, we're more than welcome to try partial fraction decomposition. So partial fraction decomposition will work here. However, I think a U substitution will also work. So let me go ahead and give this a shot. I'm going to try this by substitution. So I'm going to try U sub. If that fails, you can also try partial fraction decomposition, partial fraction decomposition. You can pick either method and get to those values. So I'm going to try my U substitution. I'm going to say U is 1 plus x, which then means that du is just dx. Okay, that's not too bad. But then this actually tells me that x, if I solve for x here, it's u minus 1. All right, so let's go through this now. So this is going to be the limit as a is approaching -1 from the right hand side. This is going to be from a to 2, and now the x value is u minus 1, so that's u minus 1. Denominator is at u squared, and dx was at du. There we are. So the limit as a goes to -1 from the right hand side for that integral as we're approaching a and 2. All right, now this is actually going to simplify quite nice because now the denominator is just a monomial, and when it's a monomial, it's actually way easier to evaluate. du. There we are. And let me keep working to the right here. So this is going to be the limit as a is approaching -1 from the right hand side. This is going to be for the integral from a to 2, and this is going to be what, 1 over u, I believe, minus this is going to be u to the power of -2 du. Let's evaluate. Limit as a goes towards -1 from the right hand side. And actually I'm evaluating, so I don't need the integral sign. The first part, the first evaluation is going to be the natural log of the absolute value of u. The second one, we add the exponent, so we add 1, so that's going to be -1, and then we divide by that new one, which means it's going to be plus u to the power of -1, and that's going to be from a to 2. And let's back sub now. Back sub means back substitution. So working with my back substitution, u was at 1 plus x, there we are, plus, and then this piece here is that 1 over 1 plus x, there we are, and this gets evaluated from a to 2. All right, let's keep going. This is going to be the limit as a goes towards -1 from the right hand side. And this is now the natural log of, let's substitute in 2, so that's going to be the absolute value of 3 plus 1 over 3 minus the natural log of 1, absolute value of 1 plus a, plus 1, or sorry, minus in that case, 1 plus a. Now let's see what's going to happen. All right, so as we can see this, we're going to go through this process. All right, so that's going to be a constant, that's going to be a constant, so those don't essentially matter here. What we are looking at is this natural log. So my a value is approaching -1, so this value is approaching -1, but it's approaching it from the right hand side. All right, so we're getting values of that are close to -1, but they're slightly, let's say, slightly larger in a sense. All right, so they're going to be something like -0.9, -0.8, -0.7, -0.99. So looking at all those values, this is always going to get me a positive, and it's going to get me positive really close to that natural log of that value of, let's say, 0.001, 0.000001, so on and so forth. That means that this here is going towards -infinity. So this here is going towards -infinity. This here is then going to go and we'll go through that process again. Negative value, -1 from the right-hand side. So these values are going to be smaller than these, but they're going to be approaching -1. So they're practically going to be 0, which means some sort of infinity. But then do we need positive or negative? Well, these values here are going to get us some positive infinity, because again, 1 is always going to be larger here. So here we get some sort of positive infinity. Great. Now that we've seen this, we can now start going through our process. Well, which one of these is going to go there faster, right? In this case, the natural log will get there this will get there faster. So when we have this, we're going to get the natural log of the absolute value of 3 plus that 1/3, and then we get some sort of infinity here. So getting that sort of, let's say, infinity will now get us that positive infinity and negative infinity. Now remember, these infinities, we got to be careful though, because they're not always going to be the case, right? As we saw back in chapter 6, when we were dealing with L'Hopital's rule, we were able to then extract which one will overtake the other, if it's possible. All right. Now for this, we're actually going to say that this is going to go towards negative infinity, which means at the end of the day, this is divergent. So this integral, the integral that we started with from -1 to 2, and that was for, wow, I already forgot the value. There we go. And that was for x over 1 plus x squared dx. This is equal to infinity, so it is divergent. There we have it. So that was part A, where we got a divergent integral. Let's look at part B. Part B, we want an integral from 0 to 9, and this is going to be for 1 divided by the cube root of x minus 1. And that's all going to be dx. So again, because the limits aren't going towards infinity, this is a type 2 improper integral. We could use our u substitution here. I'm going to say use u sub. If you use a u substitution, it's a pretty straightforward evaluation. All right. Now, the reason I say it's a type 2 integral, improper integral, is because this in here has a discontinuity. The function f of x is equal to 1 over the cube root of x minus 1 is not continuous at x is equal to 1, and x is equal to 1 is within that interval from 0 to 9. So how do we alleviate this? Well, we alleviate this by using the limit argument. All right. Now, I'm actually going to back up really quick. We actually alleviate this by setting two types of integrals. And here's the integrals that we want to set up. From 0 to 1, and 1, we'll see what happens in a bit. 1 to the cube root of x minus 1, and that's dx, plus from 1 to 9, for 1 over to the cube root of x minus 1, and that's dx. So notice, what I did was I used a property from Calc 1 that said we can split up our integral within our domain so long as we keep the bounds of integration the same. Now, when we do this, we're then going to split this up because this first integral is going to stop at this 1, but it's going to stop at this 1 for the interval from 0 to 1. That means we're going to approach 1 from the left. So this is going to be the limit as t is approaching 1 from the left-hand side, and this is going to be from 0 to t. for 1 over the cube root of x minus 1 dx, plus this other integral needs a limit. Let's choose a different t value. In this case, let's choose the limit as a goes to 1, and since this interval goes from 1 to 9, 1 is on the right-hand side, so this is going to be approaching 1 from the right-hand side, and that's going to be from the integral from a to 9. You know what? I don't want to use a because I'm already using 9, and it might get a little convoluted. All right, so let's choose n. There we go. That's better. That's going to be the cube root of x minus 1 dx. Now all we have to do is just use a u substitution. So use a u substitution for these two integrals and we'll be able to extract that portion that we need. So let's go through and let's do that u substitution. All right, we said we wanted a u sub, so u is equal to x minus 1. Nice. That means that du is just dx. Pretty good. So this is the limit as t is approaching 1 from the left side, from 0 to t. And this is now going to be, and actually I'll rewrite this differently. This is now going to be u to the power of negative 1/3, and that's going to be du, plus the limit as n goes to 1 from the right-hand side, and that's going to be from n to 9. And once again, that's the same integral. There we are, and that was du. Perfect. So let's go through and let's evaluate that integral. One from the from the left-hand side. So I'm going to add 1 to this exponent. So adding 1 should get me 2/3. So that's going to be u to the power of 2/3 multiplied by its reciprocal. That's 3/2, and we're going to evaluate from 0 to t. Same thing here. Limit as n goes to 1 from the right-hand side, and this is going to be 3/2 multiplied by u to the power of 2/3. And that's going to be evaluated from n to 9. Let's keep going. This is going to be the limit as t is approaching 1 from the left, but now I need my u values to be what they exactly were last time. So this is going to be 3/2 multiplied by x minus 1 to the power of 2/3, and we evaluate from 0 to t, plus limit as n is approaching 1 from the right-hand side, and oops, excuse me. Here I am talking about that back substitution, and I failed to do so there, but it's okay, got it now. There we go. So now that we have these integrals or these evaluations set up, all we need to do is go through and evaluate using the limit arguments. So let's see if we can go through and let's see if we can evaluate using those limit arguments. And that was, there we are. So that's going to be 3/2, and this is going to multiply t minus 1 to the power of 2/3 minus evaluating at 0. So that's going to be negative 1 to the power of 2/3. Nice. Plus the limit as n goes to 1 from the right-hand side. And, ooh, excuse me. Did I substitute? Yeah, I substituted in t there. Okay, good. Sorry, my apologies. I thought I missubstituted a value here. But we're all good so far. 3/2 multiplied by, that's going to be 9 minus 1, so that's going to be 8 to the power of 2/3. And then minus, that's going to be n minus 1 to the power of 2/3. All right, so let's go through and make our substitutions now using these limits. So the limit here, as it's approaching 1 from the right-hand side, well, it's going to approach 1 from the left-hand side, which there is no discontinuity here, and because there is no discontinuity, it's just going to evaluate to 0. Same thing here. Limit as n is approaching 1 from the right-hand side, there is no discontinuity, which means this part here gets me 0. So what are these limits evaluating into? Well, this in here, well, let's see if we can go through. That's going to be the cube root of -1, that's -1, square that, that's just going to be 1, so that's going to be -1, nice, plus this limit here, let's see if we can evaluate this limit here, so it's going to be the cube root of 8, the cube root of 8 is 2, so that's going to be 2 to the power of 2, that's going to be 4, so that's going to be 3/2 multiplied by 4, and I forgot one piece of information, guys. See, this is why I like being in class with you all, because you guys keep me honest. We forgot to multiply by that 3/2 here, so it's 3/2 multiplied by -1. There we are. You guys keep me honest in class. So now this turns out to be -3/2, and this turns out to be, what is that, plus, let's say, 12/2, because now we can just add them together and we get 9/2. So my question to you, is this type 2 integral convergent? Yes. Yes, it is. So, the integral from, and where was this, from 0 to 9 for 1 over the cube root of x minus 1 dx is convergent, and it is 9/2. And there you are, all done. Perfect. So again, some of these integrals take a little bit of time to work with, but the argument should still be there. We cannot assume that because there's a discontinuity, the limits will always cancel like this out. They will not. We have to be very careful with that, and you have to go through the arguments showing the limit arguments that you're using. All right, so be very, very mindful of that. Now, the third type of improper integral that we want to look at is going to be an integral where we compare some values. So I'm going to really quickly throw up that definition on here on the screen. That way you can see it. So you'll see it in just a bit. So here's where we start looking at the comparison theorem. And the comparison theorem kind of works along the lines of that sandwich theorem that we learned back in Calc 1, otherwise known as your squeeze theorem. Now, that squeeze theorem basically said that you have to bound some function from above and below, and as it's approaching a limit, then if your function is bounded and you can find the limit of the two bounded functions, then the third function that's in between them must converge to the same number as they're kind of converging to that point. So, how does that work with what we want to look at? Well, as you see here, we're going to assume one thing, and we're assuming two things. One, that both functions are continuous. Secondly, that f of x will always be larger than g of x, and that that's always going to be greater than 0 for some x values that we choose. So, if the improper integral from a to infinity is convergent, then so is g of x going to be convergent as well. All right, that just means that f of x was above it, and as we integrated, that function converged, meaning that area got really small, and g of x was below it, so it must have converged as well. If g of x is divergent, so if g of x is at the bottom and it's divergent, well then f of x is right above it, then it must also be divergent. So these comparisons are going to help us to determine what is the value that we want to look at. All right, so we're going to go through some examples here. We're going to use the comparison theorem to determine whether, whether or not the integral is convergent or divergent. And the first integral that we want to look at is going to be from 1 to infinity for 1 plus sine squared of x divided by the square root of x. And this is all going to be dx. All right. Whew. Here we go. All right. So, as we start looking at this, again, we're going to want maybe some comparison to see what we can find, all right, or what we can work with. So since they're telling us to use a comparison theorem, we're going to use a comparison theorem to either converge or diverge for this integral. So if it's going to be convergent, then I want to choose some function above this. That way it'll converge. If it's divergent, then I want to choose some function below it. All right, so I'm going to go through a quick process. So my process is going to be to try to find that comparison. So try to find a comparable function that is, I'm going to put this in quotations, easy to integrate. And the reason I put easy in quotations is because easy doesn't mean exactly easy. It just means that it is integrable under the techniques that we've learned so far. So let's identify the function that we have so far. The function that we have here is 1 plus sine squared of x divided by the square root of x. All right. So looking at these two functions, awesome. Or sorry, I said these two functions. Looking at this function, awesome, great. So I need to develop another function. We'll call this g of x function. All right. So let's see if we can develop a function here, and I'm going to make that in, I don't want orange, I'll make that in, yeah, let's do this color. So I'm going to say g of x. Now I'm looking at the numerator here. Look at that numerator. 1 plus sine squared of x. Typically, sine values are easy to bound because sine values are bounded between -1 and 1. Now, I want you to think about all those values between -1 and 1. All of those values are just some rational or irrational functions that are less than 1 but above 0. Because of that fact, any time that we square them, we're going to get an even smaller number. So when we're looking at sine squared, we're looking at fractions that are going to be small in the sense that they fit in the interval between -1 and 1, or in this case, because it's squared, 0 to 1. What's the largest this could be? Well, the largest that sine could be is 1, so 1 squared is 1, which means the numerator can be 2 at most. The denominator, I'm going to keep it as is, square root of x. Specifically because if I want to find this comparable function, this one is actually going to be easier to integrate versus this one. All right, so which one's larger? Well, looking at this comparison, I think this one over here, I think this one over here might actually be larger. And that one's larger, or it could be equal to, and it will be equal to whenever this here is 1. All right, nice. I like this so far. So we found a function, g of x, that is larger. Great. All right, awesome. So let's go through and let's see if I can integrate this, and let's see once we integrate what will happen. All right, so I'm going to go through the integral here for g of x, and I'm going to want to go through 1 to infinity, and this is going to be dx, so that's going to be from 1 to infinity, and that's going to be for 2 times the square root, or in this case 1, or whoops, in this case x to the power of -1/2, and that's dx. All right, So using my arguments, I say t is going to go towards infinity here. So t heads to infinity, and that's from 1 to t, and this is going to be 2x to the power of negative 1/2 dx. There we are. So now that's the limit as t goes towards infinity, and this is going to be 2 times, let's say, x to the power of 1/2. So that's going to be, what, a 4 here? There we are. So that's going to be 4, evaluated from 1 to t. Perfect. All right, so then that's going to be limit as t goes towards infinity, and that's going to be 4 times t to the power of 1/2 minus 4. But there's an issue. This diverges. So the issue being here that if this function is bounding above this function, then if this one diverges, it tells me nothing about f of x. So we have an issue. The function that we chose diverged, but the function that we chose was above. Youch. Okay, so back to the drawing board and see what we can do. All right, that was easy to integrate. I like that. Now, let's see if we might have bounded this slightly different, or let's say if we would have chosen a different bounding. Let's say that if I bounded this below by 1 over square root of x. Does this inequality hold? Yeah, because again, these values oscillate between 0 and 1. 1 being the largest, 1 being the smallest. Which means if 1 is the largest, that means it could be 2. So that means 2 is greater than 1. Awesome. Denominators, non-comparable because they're the same. And if it's 0, then it's 1. That means they're equal to, which means this works. But according to the work that we did here, so from that work here, guess what happens? Yeah, this function also diverges. So the integral from 1 to infinity for h of x diverges. And this is what we want, because now we bounded the function in question from below, and we got that function from below to diverge, which means the function above it must go with it. So the comparison that we made here, we're going to use h of x as 1 over the square root of x, and h of x is smaller than or equal to, or less than or equal to, than 1 plus sine squared of x over square root of x, and this was our f of x. Since the integral from 0 to infinity, and it was from 0 to infinity, no, from 1 to infinity, sorry, my apologies. The integral from 1 to infinity for the square root of x dx diverges. So does the integral from 1 to infinity for 1 plus sine squared of x dx. Oops. Square root of x dx. There we are. That's it. That's all we got to say. Let's try part B. So part B. We now want to identify the integral from 0 to infinity for arctan of x divided by 2 plus e to the power of x dx. All right. So again, the process is that we need some comparable function for this. All right. So we need some comparable function, and we're going to try to get those comparable functions to occur. Whew. All right. So let's see. Arctan, that's just inverse function, which means we're looking for angles, and they'll be evaluating angle-wise. So let's look at this. I want to build maybe some comparison, and I know that arctangent will have some bounds, simply because, let me look at these bounds here. I'll write them in red. Remember, arctangent is tan inverse. And tan inverse, if you remember, is bounded by two different values, one of them being pi-fourths and the other one being positive pi-fourths. So because they're bounded by these two functions, or by these two values, I'm going to be able to use these two values when I'm figuring out what comparison I should be making when I'm looking at this function. All right, so here we go. So as I'm looking at this comparison, I want to make sure I grab the correct function. So as I'm looking at this, pi divided by 4, I'm going to be able to get some good values out here. So let's try this comparison here. I want arctangent of x to be divided by 2 plus e to the x. And we'll see if we can get some functions here to help us out. So I'm going to say the comparison that I want, we can bound it from above, and let's see if bounding from above works. I want to use pi-fourths up here. So I'm going to use pi-fourths as the bounding for arctan up there. And then that's going to be divided by 2 plus e to the x. Nice. So pi-fourths, that's radians. We could work with pi-fourths here and everything would be spectacular. But I think I want to work with something else a little bit easier. So, and the reason I say a little bit easier, I'll write this in a different color here. I'll say note. Pi-fourths is approximately 0.785. And so what I want to do is I want to get something larger than that. I want to get something larger, and let's go with 2. 2 is definitely greater than this, therefore 2 must be greater than this. There we are. Now, I want a different function now, because even though this function is easy enough to integrate, that's awesome. But there's actually something else quite nice about this. Check this out. What happens if we do this? Is this function 2 divided by e to the x larger than 2 divided by 2 plus e to the x? Yeah, because we're adding 2 to the denominator here, it's smaller than this fraction. Is this one easier to integrate? Yes, it is. Let's look at that integral. I'm going to call this g of x. So let's look at the integral from 0 to infinity for g of x dx, and we're going to see if this holds. All right, that's going to be the limit as t goes towards infinity, and that's going to be the integral from 0 to t. G of x was 2e to the negative x dx, which means this is limit as t goes towards infinity, and that's going to be a constant, so that's negative 2e to the negative x, evaluated from 0 to t. This means limit as t goes towards infinity. This is negative 2e to the negative t plus, because that's going to be a minus, 0, so that's going to be plus 2. There we are. Which means this limit, send this off to infinity. Because it's negative, that's going to be in the denominator. Therefore, that all is going to go towards 0. And all we're really going to be left with is dos. Which means, is this integral convergent? That's a big question. Well, yes. Yes, it is. By the comparison theorem. We found here a function that is bounding our initial function from above. It's bounding it from above, and if it bounds it from above and the above function converges, then so must the function below it. So let's write that up. All right, so I'm going to say since arctangent of x, or actually, yeah, arctan of x divided by 2 plus e to the x is less than or equal to 2e to the negative x, and the integral from 0 to infinity for 2e to the negative x dx converges, then so does the integral from 0 to infinity for tangent inverse of x, or arctan, of 2 plus e to the x dx. And that's it. That's all there is to it. Now, finding the function that will be able to be comparable, that is the hard part. It takes some time to go through it. And as you saw me working here, if this didn't work, then what I would do is I would go backwards and I would try to use the lower bound to see if I can bound it from below. So always try to do that. Same thing happened here. I bounded it from above initially. It didn't give me what I wanted, but then I said, hey, I can then bound it from below, and the same thing will still process. Which means here, again, I was in that same argument. I chose the bounding from above. Luckily it worked, but if it didn't, then I would go from the bounding from below. All right? So that's it for the improper integrals, and then I will see you all next time. So stay on top of doing your homework and stay safe. I'll see you all.